Well, let me officially open the final session on hot particle coupling. I'm just going to skip the introductory remarks because we are running rather late. We have approximately an hour left, and I think we'll get through another 3 talks if we try hard. So let me just say that the topic of hot particle coupling has been very controversial in the last few years, and I hope that at least some of those controversies will be sorted out in the next day and a bit. Well, let me call on the first paper, entitled Anomalous Resistivity and Non-Thermal Features in the Auroral Plasma. In the abstract, it's listed under Papadopoulos, Coffey, and Ossakow. The talk will be given by Dr. Ossakow.
The concept of anomalous resistivity has been floating around the plasma physics community for some time now. It has been invoked in a number of situations in the coupled magnetospheric-ionospheric system. In particular, recent papers on auroral arcs have made use of the idea of anomalous resistivity, and it's been mentioned quite a bit during this meeting, sort of as a panacea to all problems. This talk will be broken up essentially into 2 parts, one giving a broad introduction to anomalous resistivity, and the literature on this subject is quite voluminous, and I must apologize for anybody whom I leave out. The second part of the talk will address a new type of calculation pertaining to anomalous resistivity for auroral plasmas, in which a description of the calculation will be given, and it's been motivated by recent experimental results. Can I have the first slide, please? Well, let's see. Under the influence of an electric field, essentially, electrons acquire a drift relative to ions, and in the absence of collisions, nu equal to 0, they will just freely accelerate and run away. If we use a simplified equation here for the average velocity of electrons along field lines, we can see that this is the solution when nu equals 0. This free acceleration is usually called runaway. With collisions, you balance essentially this force against that force, and you come up with an average drift velocity of this, which is using the classical electron-ion collision frequency, usually denoted by the Coulomb collision frequency. It's essentially binary encounters, and it has this form where log lambda is essentially the plasma parameter, the Debye length divided the log of the Debye length by the distance of closest approach, and t to the 3/2 power in the denominator. And the classical resistivity from all this can be defined in terms of E naught over J, and you can have E naught over NeV average essentially, and if you plug in the electron-ion Coulomb collision frequency, this is what you get for classical resistivity. This is true as long as the electric field is less than the so-called runaway field, and this runaway field was shown in the Fokker-Planck calculation by Dreiser about 15 years ago, in which if you just included classical electron-ion collisions with just the binary encounters with no wave phenomena, if your applied electric field was greater than this runaway field, then all the particles would just run away. You would have no resistivity at all. Essentially, you can see that this is the electron-ion collision time, and the V sub E is the thermal velocity. So if the electrons obtain a thermal velocity in electron-ion collision time, there's essentially nothing to stop them from running away. The classical Rutherford cross-section goes like 1 over the energy squared, and so the classical cross-section goes to 0. Anomalous resistivity can be defined analogously to classical resistivity. Instead of nu EI, we put in nu effective, where nu effective is some effective collision frequency due to interactions of waves and particles, either direct or indirect, as we'll see later on. And so you can define a parameter beta, which is essentially nu effective over nu classical times eta classical, and this parameter beta will essentially tell you what the enhancement, if any, of classical resistivity is. Essentially, what's happening is that the nu effective comes from a drag force due to waves. The usual phenomena is wave-particle interaction, which people look at, and essentially the waves act as a drag on the medium, you apply an electric field, you get a velocity or a current, and the waves that come unstable due to the current, say, then react back on the distribution function to give you an average velocity so you don't get free acceleration, and so that the wave-particle interactions sort of act against the applied electric field. And essentially, this creates a steady-state situation, so you do not get any runaway phenomena. Can I have the next slide, please? The next slide, we will talk about the usual streaming instabilities. That's it. In which you essentially have a current along the magnetic field, and this current essentially creates the instability. You have when the average velocity of the electrons or the relative electron-ion drift is greater than the electron thermal velocity. This is the Bunemann two-stream instability. And you get a growth rate of the order of ME over MI to the 1/3 times the plasma frequency. This is a very strong type of instability. It's a non-resonant type of instability. It's really a fluid type instability. The other is the famous ion acoustic instability, and that requires really that TE be much greater than TI. 10 will do. And the drift velocity has to be greater than the sound speed, but less than the electron thermal speed. And you get growth rates of the order of ME over MI to the 1/2 times the plasma frequency, the electron plasma frequency. So these growth rates are lower than these. If you have TE of the order of TI, another interesting instability is the electrostatic ion cyclotron instability. And essentially, once again, drift velocities above the ion acoustic speed, but below the electron thermal speed. Growth rates of the order of 0.1 to 0.3 times the ion gyro frequency. So these are even slower than the others. Actually, the last instability will be discussed by Dr. Palmadesso in a talk to be given after Dr. Bloch. The importance of the electrostatic ion cyclotron waves was first pointed out in topside ionospheric studies done by Kindell and Kennel a couple of years ago. And they pointed out that it was an obvious candidate for anomalous resistivity because the average drift velocities that they calculated seemed to fall into the regime of ion cyclotron turbulence. Also, the factor that's very important is that for T of the order of TI, the ion acoustic wave, unless you are considering very different types of distribution that are different from Maxwellian, will not go. There are quick ways of finding out the anomalous resistivity in plasmas. One can do back-of-the-envelope calculations in which one essentially sets nu effective equal to the growth rate. But this is not really a complete calculation, and there have been other modifications to these things. Complete calculations involve actually solving the nonlinear system of equations. And in general, what I've been speaking about so far usually looks at the plasma as an infinite homogeneous medium and looks at the time domain of the system. However, it's not obvious in magnetospheric ionospheric systems that one can completely neglect the inhomogeneity of the plasma. And indeed, this will be brought up in the study of the electrostatic ion cyclotron turbulence and resistivity by Pete Palmadesso. We will show some examples of anomalous resistivity so that one does not believe that it's a figment of a theoretician's imagination. It's difficult to show in space experiments, I guess, because one can't put a voltmeter on a field line. But the following slide is a clear-cut laboratory experiment, which I would like to show, in which one can essentially change the electric field at one's will and measure things very simply by putting voltmeters outside and stuff like that. Can I have the next slide, please? Well, this might be a little hard to see. This is a slide from paper of Hamburger and Friedman. Essentially, this is the classical resistivity. It also shows some Russian results. These measurements were done in toroidal geometries. Essentially, they applied an electric field, and this is the conductivity. Classical conductivity, there's a decrease in the classical conductivity, there's an increase in the resistivity as the electric field becomes a certain value. There's a type of plateau. As they increase the electric field further, they get another increase in resistivity, so that there are two anomalous regimes that they see here. This is purported to be, under their conditions, the ion acoustic regime, and this is purported to be the Bunemann regime. Can I have the next slide, please? There's also all sorts of theoretical computations that have been done. This is one which is fairly old, 10 years now, Field and Fried, a quasi-linear calculation in which they had an infinite homogeneous plasma, applied electric field greater than the runaway field. They noticed that the current starts to increase. It reaches a certain time where wave-particle effects take over, start to create a drag on the plasma. It starts to decrease, attains an asymptotic value in which you have a steady-state current. These two types of calculations were done for different things, but the important thing to note is that after a certain free acceleration time, the current turns over and starts to level off due to collective phenomena. That is, the wave particles and the instabilities. These instabilities were all in the ion acoustic regime. They were considering temperatures much greater, electron temperatures much greater than ion temperatures. Can I have the next slide, please? And then finally, the last bag is the theoretician's experiment, particle computer simulations done by Joe Orens in his thesis in 1973. This is the current. This is versus plasma periods. There is, essentially, he drifts at first to increase the level of fluctuations. These are for different values of magnetic field. As he increases the magnetic field, the current comes down. Or rather, the current goes up. This is the increase of magnetic field. So as he increases the magnetic field, the current tends to look like it's going to run away. This was also pointed out by myself and Fried about 8 years ago, that if you went to infinite magnetic field in the ion acoustic regime, you would have no more anomalous resistivity. And here essentially is his basis, his resistivity as a function of magnetic field, so that as he increases the magnetic field, the resistivity goes down. Classical is somewhere around here. He's in a very tight parameter regime. Well, so far I've been talking about current-driven instabilities creating the anomalous resistivity, so that the waves are generated by the currents, and the waves then react back on the drifts. That is, the electron distribution function is altered, and we create a constant current situation and anomalous resistivity. But what about the case where you already have developed an enhanced level of fluctuations? Can we scatter particles from these waves and create anomalous resistivity? This is where we have a current which does not itself create any instabilities, but merely reacts with the already existing enhanced thermal fluctuations. That is, there is a highly non-thermal collisionless equilibrium present. We will focus our attention on the auroral plasma and essentially ask two questions. One, can we get the enhanced density fluctuations? What is the value of the enhancement that they will produce in the resistivity, if any? The model which is presented is motivated by the recent experimental results of Reasoner and Chappell. If I can have the next slide, please. Next slide, please. And this is their results. These are part of the results from the May '73 issue, I guess, of the JGR. Essentially, you notice that you have a sort of a Maxwellian tail coming out, and then this is the weak beam, and this is the other side. It's the backscattered. So that you have an ambient plasma, what looks like wasn't an ambient plasma, tails coming out, and a weak beam. And this seems to be a stable configuration at about altitudes of about 700-800 kilometers. And they seem to see this quite a bit. Can I have the next slide, please? This slide essentially shows what's happening, which can explain those results, and which we will get our anomalous resistivity from. The initial state is assumed to be the following. You have a weak beam and a main ambient plasma. You have a V thermal of the plasma, delta VB of the beam, and N sub B of the beams, and the density of the beam is very much less than the background plasma. Essentially what happens is this beam creates plasma oscillations over here. These plasma oscillations, by a nonlinear phenomenon known as the parametric instability, or in this particular case, the oscillating two-stream instability, these waves decay into regions over here at plasma frequency waves, and over here, symmetric about the distribution function, plus zero frequency or low frequency ion density fluctuations. The final state that one gets is this state here, very reminiscent of the results of Reasoner and Chappell. And what's happening is that the waves with the plasma frequency here are electron landau damping the tail, so they're getting dragged out on both sides. And the energy from the beam is being shuffled out of this resonant region of the beam into the non-resonant region with the ambient plasma. Essentially, the time for this to happen is greater than the quasi-linear relaxation time of the beam, so that the beam does not flatten according to quasi-linear theory, but rather one gets this quasi-equilibrium state where you have superthermal tails, a weak beam part, and an ambient plasma. In the frequency domain, you have this main wave 1 sort of cascading into waves 2 and 3. You have a main wave near the plasma frequency. It cascades into a wave just above the plasma frequency plus 0 frequency ion density fluctuations. Essentially, the condition for instability of the oscillating two-stream is that this condition here, E naught squared over 4 pi nt, be greater than 4 nu EI over omega E. This nu EI can also be the Landau damping of the waves in this region. Essentially, this E naught is the field that is driven by the beam. The beam drives plasma oscillations due to the beam plasma instability. And this is the E naught. You have an E naught cosine omega 0 t factor there. How many more minutes? 2 more? Or what? Oh, 2 more minutes? Okay. Well, then I'll have to skip over the next few slides, I think. Let me just get to... this essentially explains it, but we'll skip over that. That essentially, well, explained how the normal modes change in the system to describe the oscillating two-stream instability. Anyway, the point is you can calculate an effective, collision frequency from this formula here. If you look at this kinetic equation for the electron distribution function, D essentially contains the enhanced density fluctuations that you're talking about. And V drift is just the average drift velocity in the electron frame. So let me go on, since I only have 2 minutes. Essentially, these formulas can be extracted from the previous formulas, and you have the dielectric constant of the electrons. You have the drift velocity, essentially, of the current that you're looking at is much less than the electron thermal velocity. Finally, due to this oscillating two-stream instability, you get a new effective that looks like this, in which W is essentially the wave energy in the low frequency ion density fluctuations. You have to remember that your drift velocity of the current system that you're looking at is very small compared to any instability velocity. It's not going to create an instability. The K lambda D bar is essentially the average wavelength of the system of the oscillating two-stream instability. Okay, I'll just go on to the next one then. Unfortunately, we want to know what the energy is in the low frequency density fluctuations, but really the beam plasma instability and the oscillating two-stream, I should say, instability will tell you what the density fluctuations are in the electron plasma oscillations which create the tail. And from a simple formula like this, we can relate the two so that we finally get a new effective which looks like this, which is related to W0, which is the enhanced electron plasma oscillations which create the tail. Now, W0 is of order n beam times the mass of the electron times V beam times the width of the beam times an alpha, where alpha is less than 1. And this has been borne out by two-dimensional, one-dimensional computer simulations of the oscillating two-stream instability. Effectively, then, your new effective becomes the following. It has the following dependencies here. What is to be pointed out is that new effective is independent of the drift velocity of the current that you're looking at, the low drift velocity system. It is proportional to the beam energy, V beam over V thermal squared of the main plasma. It is proportional to n to the minus 1/2. Actually, this shows n, but there's an n and a square root of n up here, so that it's smaller at lower altitudes. Now for looking at the actual auroral ionosphere, we can use the following parameters. We have a delta VB over VB of about 1/3, a V beam over V thermal of the main electron about 200. Now this corresponds to a 10 keV beam and about a 3,000 degree Kelvin background plasma. For K bar lambda D, we take this 0.15, which is the maximum instability growth rate of the oscillating two-stream instability, so that we get a new effective essentially that looks like this. This is the alpha, which is somewhat less than 1. We relate this to new classical, where we've taken, as I said, 3,000 degrees for the background ambient type of plasma, and the beam density to be about 2 times 10 to the minus 2, so that we get this beta, this new effective over new classical, to be this point here, 1.2 times 10 to the 9 times alpha times n to the minus 3 halves. And for parameters in the auroral plasma, where you can take this to be about 10 to the 3 at, say, 1,000 kilometers, you get an enhancement of 10 squared to 10 to the 4th, depending on what density you put in there. Well, thus, I'd like to say that we have demonstrated that the existence of enhanced low-frequency turbulence due to instabilities produced by field-aligned streams of high-energy precipitating electrons in the auroral zones can significantly increase the value of the plasma resistivity, even when the plasma is stable with respect to current-driven instabilities. These results will appear in forthcoming letters by Papadopoulos and Coffey, both on the non-thermal features of the auroral plasma and on the anomalous resistivity. And we're currently trying to actually solve the nonlinear set of equations numerically, and also doing some particle computer simulations to look further into this instability in the final nonlinear state.
Yeah, two questions. One, I don't quite understand how this distribution can be stable, where you had in the tail a derivative, the FdV, which is positive.
Yes, well, the point is the following. You have that, but it's you see, it's nonlinear. It's the fact that the wave energy is being pumped out of that region and into the tail region where it's being Landau damped and causing the superthermal tails. And this configuration is stable.
But doesn't it then at the same time shift according to the, what is it, Drummond Pines or?
No, you see, the point is that you're not quasi-linear stabilizing this system. If you were to quasi-linear stabilize the system, the beam would flatten out entirely. But the point is that the oscillating two-stream instability is happening on a time scale much faster than beam stabilization by quasi-linear theory. And what this produces is a quasi-thermal equilibrium where you have, well, it's quasi-non-thermal. It's a non-thermal equilibrium. We have superthermal tails on each side and a remnant of a beam, a weak, fast beam. This is a stable situation.
Okay, another question. On the preceding slide to that, you had an expression, I think W0, yeah, right. There. What is it? W sub 0 is proportional to N sub B, M, V sub B, delta V. Right, that expression. Now, either I missed it or you didn't say it. I don't know. What is that? The energy lost by the beam?
That's essentially the beam energy, the available energy from the beam.
Well, it's lost. I mean, it's a rate at which the beam loses energy. Now, where does that go into? That's my question.
The beam loses energy essentially by going into these enhanced ion density fluctuations and the enhanced plasma fluctuations which reside in the tail region of the plasma. In other words, there's a shift in phase velocity from the high beam phase velocity electron plasma oscillations to lower phase velocities, which then affect the tail. That's where the energy goes.
Okay, so
it's essentially what's happening is you're essentially taking the energy in the resonant region and cascading it into another region. So the point is that the energy is not there to interact with the beam anymore. It's gone. It's somewhere else.
Okay, thank you.
I'd like for you to amplify further on a couple of points. First of all, in your first order Boltzmann equation, you had the V cross B naught term, and is that really significant in these calculations? No. Okay.
I just wrote down the general equation, and what's important is the right-hand side, which essentially is a collisional term. But what I meant by collisions is all collisions: particle-particle, wave-particle, and any sort of enhanced fluctuation effect, etc.
Okay, and then in a little throwaway comment, you said that for first order work, you could set the effective collision frequency equal to the growth rate.
Yeah, the point is that what you really want to know is what's the saturation level of the waves. Mm-hmm. Well, you're not going to get that until you do a nonlinear calculation. Right. But in lieu of doing nonlinear calculations, people say, well, what is the effective collision frequency? Well, it must be the growth rate of the wave. It's not entirely true, but you can get a handle on things. If you don't get enhanced resistivity from that, you're not going to get it from anything.
Mm-hmm. Is this cascading of the wave energy, is this a similar sort of process to what Derek Perkins has been talking about in regard to studies with Arecibo radar?
Rip Perkins, yes. He's,
Yeah.
actually, he's looking at
Rip
electromagnetic parametric instabilities. He's essentially, I think, looking at electromagnetic, where his electromagnetic wave goes up there and then decays into plasma waves.
Right.
This is an entirely electrostatic process. The beam essentially creates electrostatic plasma oscillations. And those oscillations decay into other electrostatic processes.
Okay.
This is entirely electrostatic. There are no electromagnetic effects in here. Essentially, curl E equals 0.
Thank you.
Yeah, for comparison with measurements, can you give a typical K value for the or wavelength value for these zero frequency waves, and how sharp the spectrum in K it would be?
Actually, I can't really say how sharp in K it would be. My only feeling is that one knows, for example, what zero frequency thermal fluctuations are like, and if you could measure, you have a standard formula, say, for ion acoustic fluctuations, ion density fluctuations. If you could measure what the thermal levels are and relate them to those things, which have a fairly well described K spectrum, if you get enhancement above those, then you can say that you essentially are seeing this type of instability.
Your theory doesn't pick out any particular K. I mean, you say there's a delta omega equal to 0, but it's not exactly equal to 0.
Yeah, right. The K though that comes in there is, as I say, the maximum. We haven't done the full nonlinear calculation to find out which K value is dominant at saturation. But the point is, the K lambda d bar that I used there of order 0.15 is sort of what you have. Okay, that's, in other words, according to the oscillating two-stream instability, that's the maximum linearized, if you want to call it that, maximum growth rate that one finds from the dispersion relation.
Is the tendency for that K spectrum to sharpen or just
That's also hard to answer without considering the complete nonlinear calculation. I would say that you would look for peaks around K lambda d of order 0.1 to 0.2, just on the basis of the growth rates. As I say, we're currently looking at the full nonlinear situation to find out what the spectrum really is. You have to determine that either experimentally, what you were asking me, how do you determine it? So I have to determine it for you theoretically. And we're currently doing that.
I have a question about the Hamburger-Friedman experiment. Isn't it right that this experiment is a pulsed experiment with a few microseconds duration?
Yes, as a matter of fact, most of them carry out pulsed experiments, but what's important is what is the pulse width compared to the time of what's going on. And essentially, their pulse width is long compared to the instability time and saturation of these instabilities.
Well, it is short compared to the time for a double layer to develop. And some calculations have shown that the two-stream instability asymptotically develops into double layers. Armstrong and Roberts and Burks and Montgomery and Joyce and some other people.
I'm not entirely familiar with the...
I think these experiments are of a too short duration, actually, to show conclusively that it is anomalous resistivity.
Well, I'm sorry, I could have selected many more experiments in which, one can...
But you say they're all pulsed of
well,
few microseconds duration.
Most of them are pulsed because the basic problem is to get the electric field into the plasma.
Yes. But it's much easier to produce a double layer in a laboratory.
I'd just like to find out whether I was scaling your figures correct. From the beta for your example, is it correct to say that resistance is, the resistance there is now several orders of magnitude less than the resistance in the ionosphere?
No, it's greater.
So you have 1,000 You're 1,000 kilometers, right? Or something like that.
Yeah, well, but the resistivity goes as new effect, the collision frequency. So,
Yeah,
I'm
so-
showing the ratio of new effective over new classical, and that's of the order of 100 to 10,000.
Yeah, but now if you go down and compare that new effective with new in the ionosphere, your resistance is still very small compared to ionospheric resistances, I believe. Isn't that right?
When you say
In
new,
other words, compare your new effective at
Yeah.
1,000 kilometers with, to compute a resistance there, and compare that with a resistance
you
in
mean the
ionosphere.
classical
Yeah.
electron neutral or ion neutral?
Yeah,
collision?
lower in the ionosphere.
Yeah, this-
it's
this
still
guy-
a small resistance.
Yeah, let me just say that this theory of nu EI is only true when nu EI is greater than nu EN. When you're talking about classical resistivity, it's really electron-ion collisions. It's charged particle collisions, not collisions with neutrals.
But it's still,
Right.
I mean,
I imagine, it probably is smaller.
it's a small resistance compared to ionospheric resistances, yeah.
You showed these are rocket experimental results.
Yes, Reasoner and Chaplin.
Yeah.
Yes.
What the purpose of that? I missed the point.
Oh, okay. Well, if I may be so long, you can go back.
Yeah.
Okay. Well, the point is that essentially what they have, okay, this is just drawn on one side, but take this dotted curve and flip it over. And you get something that looks like a main body that's a Maxwellian type plasma with super thermal tails drug out, and a beam configuration which is predominant on one side. Okay? And then the next
Excuse me.
point,
One curve is you have two curves.
Huh?
Two lines. One is a primary or
No. This is, but the point is that this is for velocities going the other way. So you just flip it over if you're looking in velocity space. All right? So in the next slide, I'm saying that if you start with this configuration, according to the oscillating two-stream, you get this, which is very reminiscent of what they get.
I see. I thought this low energy side has a how do you call classical calculation doesn't agree. Lot of low energy electron dominate. So that part you are going to explain. I thought, but you couldn't explain.
Explain which part?
Low energy, abundance of low energy electron caused by secondary electron and backscattering.
This one here? This one here?
Yeah.
Yeah, well, that was not the main purpose of the talk, but I'm saying that this instability will explain the tails, and it's coming out in a paper in the JGR. I'm saying that the mechanism agrees very well with their data as far as number density. You can't explain the number density in these tails on the basis of the number density in the beam, because there are more particles here than there ever were in the beam. So they had to be brought out from the main distribution. And I'm saying that the way to do it is by this oscillating two-stream instability.
Let's have one last question.
I guess I disagree with that, having gone through a lot of the calculations that were used in that paper, that the slope isn't Maxwellian. It's actually fairly closely the expected secondary ionization spectrum.
This slope here?
No, go back to your next slide, the other slide, the experimental data. The other way.
Where is it? Well, I'm going in reverse, but it's not doing anything.
Push your finger down and keep it down.
There, if on the, say, between 100 eV and 1,000, somewhere in there, that long decrease isn't necessarily Maxwellian.
That's right,
It
it's not.
reflects the spectrum of secondaries, which have been created much deeper in the atmosphere, actually emerging from the atmosphere. And you can explain the details of that spectrum very easily without any type of plasma wave
Yeah, well, this
process.
spectrum here, that's right, it's not Maxwellian, and on the basis of this instability, you can explain it as being 1 over v to the 5/3 or something.
I just point out you can explain it with purely atomic collisional processes, too.
Okay, but I'm saying that this is an alternate, I don't know about your explanation, this is another explanation, but this explanation also will take care of anomalous resistivity. And I'm saying that the point is that one should look for essentially zero frequency waves or waves in this region here of the tail which have enhanced fluctuation levels. if you find them, then you have a sure, a pretty good bet that you'll get some anomalous resistivity. I mean, you can invoke 1170 different theories to explain one experiment. And I'm saying that the point is that in the paper by Papadopoulos and Coffey, they are able to explain these number densities, the fall off, the correct slope, all on the basis of this instability.
Well, I think my own impression, I guess Andy's too, is that atomic theory and atomic cross-sections are far more certain than plasma wave theory at the present time.
Well, that's a matter of which camp you were educated in.
Yeah, okay, one comment.
Is that, yeah, you have to remember that if you want to, Peter, if you want to explain the backscattered spectrum on the basis of degraded primaries and secondary production, okay, then you have to explain also the downcoming primaries in terms of something like Dave Evans was talking about, some reflector above you. Okay, so if you want to use that explanation, then you're presupposing a potential drop above the rocket. On the other hand, at the time Chappell and I did this work, we took the point of view, okay, here's the primary spectrum, it's God-given, and we don't really care where it's coming from. All we note is that we cannot explain the 100% backscatter at a kilovolt on the basis of the then existing Walt-McDonald Coulomb collision backscatter theory. And so we were looking for, because after all of those primaries are in the loss cone. Okay, the pitch angle arranger is all loss cone. And so therefore we were looking for a mechanism to essentially act as a barrier below the rocket to prevent particles below a kilovolt from ever reaching the scattering region. So that, as I say, that sort of puts things in perspective how this whole thing developed historically. Thank you.
Well, thank you. I'd like to just make one more comment, Peter. If you allow me my toy experiment, particle computer simulations have simulated this type of instability in which you get the tails being dragged out, the beam essentially remaining coherent and that sort of thing if you look at, collisionless phenomena. So, I mean, there is some support for it aside from just plain old theory. There are particle computer experiments. Also, I have copies of these papers if anybody wants it.